In this video, we're going to be looking at the connections between kernels of ring homomorphisms and ideals. So to get started, we're going to let phi be a ring homomorphism from R to S. And we already know that the kernel of phi is a subring of the ring R. And the question that I'm going to ask is this: is the kernel an ideal of R? And I'd like you to stop the video and try and answer that question for yourself. And when you have an answer, start the video back up and you can compare your work to mine. So hopefully you did that. To answer this question, what we need to do is we need to look at this. We need to let R be any element of capital R, and we need to let A be any element of the kernel of phi, and we need to ask the question, are the elements RA and AR, do these things, are they both in the kernel of phi? And we can answer that pretty quickly and pretty easily. So let's look at this. To figure out whether or not something is in the kernel of phi, we let phi eat it and we figure out what happens to it. Well, if I look at phi of RA, that's going to be phi of R times phi of A, because phi is a ring homomorphism. But I also know that A is inside the kernel of phi, so I get this being phi of R times the zero element in S. This is because A is in kernel of phi. But 0 times anything is equal to the 0 inside every ring, and so what this says, this set of computations, says that RA is indeed inside the kernel of phi. And if we turn it around and look at AR, we get exactly the same kind of thing. We have phi of AR is equal to phi of A times phi of R, and that is also because phi is a ring homomorphism. And phi of A times phi of R is going to be 0 times phi of R, and that's because A is inside the kernel of phi, and 0 times anything is in a ring is equal to the 0 element, and so this set of calculations says that AR is inside the kernel of phi. And hence, we do indeed have that the kernel of any ring homomorphism is an ideal of the domain ring R. And that's actually a pretty important fact. So this is an important fact. It's often called lemma, in fact. So what I want to do next is I want to kind of turn the question around. By that I mean I want to let I be any ideal of R. And I'm wondering whether or not I is the kernel of some ring homomorphism from R to some unknown ring. And to investigate that question, I have to think about what I know about I and what I know about rings that involve R and involve I. And one thing that comes to mind is that we know R mod I under its coset addition and its coset multiplication is a ring. So is there a map that I could use from R to R mod I? In other words, can I find a ring homomorphism from R to R mod I with the kernel of this map equal to the ideal I inside of ring R. Now, I don't want to work very hard, so I want to kind of think about this. Here's my idea. I'm going to let pi be a function from R to R mod I be defined by the most obvious thing in the world. Pi of R is just going to be the coset that has representative R. In other words, pi of R is going to be R plus I. And the question then, the first question is pi a ring homomorphism? And if it is the kernel of pi equal to I? So let's look at those questions. Is pi a ring homomorphism? Well, let's consider the addition and what pi does to the addition. So in other words, I'm going to let a and b be inside R, and I'm going to look at a plus b, and I'm going to let pi equal that. Rather, let pi eat that element. And what I know is that pi of any element is just the coset with that particular representative. So this is going to be a plus b plus I. And that's by the definition of my map pi. Of course, I know something about coset addition. This is going to be a plus I plus b plus I. That's by the definition of coset addition. But a plus I is just pi of a, and b plus I is pi of b. And so this is by the definition of the map pi again. So yes, pi preserves ring addition. Well, the next question is does pi preserve ring multiplication? So let's look at that. Let's look at pi of AB. Well, pi of AB is AB plus I by the definition of pi, of my map pi. But I know something about coset multiplication. AB plus I is A plus I times B plus I by the definition of coset multiplication. And let's see, let's clean that symbol up. That should be by the definition of pi. And of course, A plus I is just pi of A, and B plus I is just pi of B. And so this is again by the definition of pi. And if we look at this, pi of AB is pi of A times pi of B, so pi preserves ring multiplication, and hence pi is a ring homomorphism. Well, that then brings up the question, what is the kernel of pi? So let's look at that question. Well, the first thing that I'm going to do is I'm going to think about this. Let's let R be anything inside the kernel of pi. Well, what do I know? Then I know this. I know that pi of R is equal to the 0 element in R mod I. But the 0 element in R mod I is just 0 in R plus the ideal I. So what we get is this. Pi of R is equal to 0 plus I on the one hand, But the definition of pi says that it's also equal to r plus I on the other hand. In other words, this equation is by the definition of pi, and this particular equal sign is since r is supposed to be in the kernel of pi. But we now have a nice equation that we can work with. R plus I is indeed equal to 0 plus I, but that says R minus the 0 element has to belong to I, because that's the only way two cosets can be equal to each other. Of course, R minus 0 is just equal to R, so this says R is inside ideal I. And so what we have now is that the kernel of pi is indeed a subset of our ideal R. Well, does this inclusion go the other way? Is I a subset of the kernel of pi? Well, let's let A be anything inside I. Then what I know is that pi of A is equal to A plus I, but because because A belongs to I, A plus I is the same thing as just I itself. And I, of course, is equal to 0 plus I. And let me get my reasons written here. This equal sign is, by the definition of our map pi, and this is since A belongs to I, and this is since 0 belongs to I. 0 belongs to every subring, and any ideal is a subring, so 0 belongs to I. Well, what this says, when we think about it, is that pi of A is indeed the 0 element in our target ring R mod I, so A is indeed inside the kernel of pi, and that means we have shown that I is a subset of the kernel of pi. Now, putting this together with our first inclusion, we already know that the kernel of pi is a subset of I. These two things together say I is actually equal to the kernel of pi. And so what we now have is this. We have this very important fact. If I is an ideal of a ring R, then I is indeed the kernel of pi, where pi is defined as the map from R to R mod I, and he's given by pi of R is equal to R plus I. Now, there are a couple little things that I want to make a note of before wrapping this particular video up. The first one is a vocabulary thing. We call this map that goes from R to R mod I given by pi of R is equal to R plus I. We call this map the canonical map. Canonical map. Or the natural map from R to R mod I. And by map here, we actually mean a ring homomorphism. The other observation that the other comment that I want to make is an observation. I want to observe that the canonical map pi is always going to be onto the quotient ring R mod I, and the reason why is very simple. if r plus I is an element of R mod I, that implies that R is inside the ring R, and that will imply that pi of R is equal to that particular left coset R plus I. So pi is onto the quotient ring R mod I.